Um, the negative 3 to the negative 1 power. What does the negative 1 power do? It what? It takes it to I? No. Yeah. Can the 1 not be negative? Well, no, because we got a negative, right? So it doesn't change the number to be negative. But do you guys remember when you guys were working with like a to the, oh, that's really thick. When you guys were practicing with like variables and exponents, and you had a variable to a negative exponent, and this made it a fraction. Do you guys remember that? Maybe, maybe not. If not, that's okay, because that's why we're practicing it. So what does the negative 1 do to the 3? What's it become? 1 over 3. Yep. If it helps you, you can bring this as it's 1 over 3 to the 1, but that is the same thing as 1 over 3. Okay? Does that make sense? Is anyone confused by that? So just remember that a negative exponent does not make the number negative, it flips it. And its position as a numerator or denominator, okay? And then 2 to the 0, what does the 0 power always do? That makes it 0, but it makes it 2. Anything to the 0 power will always be 1. Yeah, it will always be 1. So if yeah, you guys can plug that in the calculator. It'll tell you. Same with the 3 to the negative 1 power. It'll tell you it's equal to 1 to the third, over 1 over 3. So 3 to 0, yeah. So you guys are going to take, you press your base number. So if you do 3, or 2, I guess, but that's okay. And then caret, it's a little up arrow, and then plus press whatever button you want to be your exponent. So it's the little caret button that looks like that. Kind of like in writing, that's how people use to like insert things into sentences. For this one, it's to raise it to a power. Okay? So 4 to the negative 2. What do we do? Make it a fraction. So this is going to become 1 over 4 to the second, right? Which is also same as 1/16. Yep. Does that make sense? So real quick question. If I were to have 1 over 3 to the negative first power, what does that become? The exponent, the negative exponent flips it, remember? So it's in the denominator now, so where should it be with a negative exponent? Did you say that? Yeah, it should be in the numerator now. So this just becomes 2 to the first. Okay? And which is also just 3. Does that make sense? Okay. So number 4, it says a certain type of bacteria doubles in population every hour. Given that there were 2 bacteria to start with, how many will I have after 4 hours? So if you guys remember in the video yesterday, the launch video kind of just touched on exponentials and why exponentials are really important in the world. And a lot of the reason we use exponentials is things like this. Science uses exponentials a lot. Bugs grow or populate at an exponential rate. Bacteria splits a lot at an exponential rate. With COVID, there were a lot of instances where if you were watching the news, they would show you these graphs that were exponential, okay? So if I were to have this bacteria, let's just start with the red one here. It's obviously black and white on your paper, but the red one up here. Let's just look at that one first. If it were to split every hour, how many am I gonna, or not split, double every hour, how many am I gonna have after 1 hour? 2. Yeah. Okay, so I'm going to have 2. I'm just going to draw them like blobs, okay? And then they're going to double again after 2 hours. How many am I going to have? 4, yeah. And then how many am I going to have after 3 hours? 8. We double. So we're not going by 2s. It kind of feels like it in these first 2 hours, but we're doubling. Sorry, it should be 8. So do you notice something between each thing? How did I get from the start to the first hour? What did I multiply by? 2. What did I multiply by between 1 hour and 2 hours? To get from 2 to 4, yep, times 2. What about from 2 to 3? 2. So from 3 to 4, what am I going to multiply by? 2. So how many am I going to have after 4 hours? 16. And then the same thing will be for this little purple bacteria, okay? So I'm going to multiply by 2. So I'm going to get 2 here. And then multiply by 2 again. Get 4. Multiply by 2. Get 8. Multiply by 2. And I'll get 16. So how many in total do I have after 4 hours? I have 16. The red one split into 16. Purple one split into 16. How many do I have after 4 hours? 32. Yeah. You just add the bottom 2 numbers. We have 32 bacterias. I don't know if that's grammarly correct, but does that make sense? So this is what exponentials are going to look like, okay? It's kind of this idea of just doubling or somehow having a same rate at which we change, okay? In this instance, we're multiplying by 2 every hour, okay? And we have 32 after 4 hours, okay? All right, everyone good on the bell work? Making sense? All right, get out your notebooks, or your workbooks, sorry. We're gonna be on page 357. And then I'm gonna pass out. Yeah, they did not remember.
Oh, okay. I'm just like, I don't remember it.
No, yeah. The numbers continued on from the first notebook, or the first workbook. So yeah, kind of funky. So yeah, page 357, even though it's honestly page 4. And then the first thing I want you to do as I'm passing out these sticky notes is on that next page, 358. There is example 4. I want you to put these sticky notes over example 4. We're not going to do example 4, but we're going to do something else. We're going to do practice with some graphs, okay? That's why we're giving you some extra graphs to work. So on page 358, over example 4, stick these little sticky notes. We're going to do some practice with some graphs, but this will be a little later on. So once you've done that, just flip back to page 357, because that's where we're starting. There you go. Everyone got sticky notes? Cool. All right. So page 358, it's this page. Example 4, it says exponential graph functions. You're going to put it over this part. Just put your graphs over here. Yeah. Over that part. Okay? Yeah. And if one of them is on the side of the page, that's okay. Or you can stick them on top of each other. Then you can unstick everything. Okay. Everyone good? Okay, so today we're starting our unit all about exponential functions. this is kind of just an extension of the functions we've been working with. I mean, it's a little different than our root functions and our rational functions that we were just learning about in Unit 6. It's kind of a new concept, but again, we're still kind of doing a lot of the similar ideas, just with different functions, okay? So, an exponential function. It's a function that contains an exponent as an independent variable. So, your variable is going to most likely always be, or it will always be, not most likely, will always be as an exponent. So do you see in example 1, it's 2 to the x. It's not 2x, it's not 2 times x, it's 2 to the x. So your variable is the exponent this time, okay? So exponential growth, this occurs when the initial amount increases by the same percentage over a given period of time, okay? So just like in our bacteria one, sorry, let me flip back. It increased by the same percentage or the same amount every time. So we increased 2 times every time, okay? And then we have this idea of an asymptote. This is a fun little thing to learn about, okay? An asymptote is a line that the graph approaches but can never touch or go past, okay? So imagine you have a wall and you cannot go past that. It's like a brick wall, basically. An asymptote is a brick wall. You cannot get through that brick wall, never. Like, that brick wall is never moving or changing, okay? With each graph, an asymptote is going to be different depending on the graph you're dealing, or the function you're dealing with, okay? So, it's usually going to be written as y equals or x equals, okay? That'll be your asymptote line. It'll be a line that your graph cannot pass. So, we're going to go through this first example, and then we're going to figure out what we're confused on together, okay? So this first example, our graph is 2 to the x, okay? Remember that idea of a parent function from last unit? Parent function is kind of our basis, it's what we build off of. So in this instance, we're going to have a parent function for any base. So for this instance, 2 to the x is a parent function, 3 to the x, 4 to the x, 5 to the x, all of those are parent functions. Okay, and then they can change based on our a, h, and k, which we'll touch on in a little bit. So, looking at your graph, domain deals with what again? X. What is our domain? Same thing in the last units and the last ideas with domain. Domain is where it extends to and our x's. So does it go towards infinity?
Yes.
Does it go towards does it go towards negative infinity?
No.
Does it? We've got an arrow here, right?
Oh.
If I were to plug in 2 to the 5 million, am I going to get a number? Yeah, I'm going to get a real number, right? So our domain goes all the way towards negative infinity and it continues on all the way to infinity, okay? So our domain is all real numbers. Okay? So if you write it, oh, that's backwards. Negative infinity to infinity. It's all real numbers. You can write whichever one you're more comfortable with, okay? Does that make sense? What is our y-intercept? If you look at the graph, where does our graph go or cross out with a y? 1, right? So we can go over to our table and plug in 1 for our y-intercept. And you also have some of this already filled in, so I'll just fill it in real quick. So you guys don't have 2 filled in. Where do we plug in 2 to our equation to figure out what our f of x term is? Where's our variable? Yeah, it'll equal 4. So it's 2 to the second power. That's where we plug it in, right? And we get 4. As you can see, I think they graphed it. Yeah, 2 to the 4 is right here, okay? So all you do with these exponentials is you plug in your x, so any of these values, and they're always going to go in the exponent. They're always going to go wherever your x is in the exponent, which your exponents may look different, as we're going to see in the next page. What's our range? This is what's going to be a little different about exponents. What is our range? Yeah.
So
Not 1, but think about where is your graph not going past in your y's. Four? Well, y's this way. Yeah. Sorry. So our graph extends towards infinity, right? Like we all agree that that's going to continue on towards infinity. But going down towards negative infinity, does it look like it doesn't pass something? Yeah, it doesn't go into the negatives. So our asymptote in this instance is our 0. It's our y or our x-axis. Okay? So our asymptote is going to be y equals 0, which then we can use in our range. Where does our range start and go to? We never go past what? 0. And it goes towards infinity. So our range is going to look like this. It's usually going to either start with or end with your asymptote with your range, okay? And then our end behavior, this is just something we want to touch on real quick just because you guys have been working on it so much. But our end behavior, as x goes towards a negative infinity, where does f of x go towards? As x goes towards negative infinity, where is f of x approaching? Not positive infinity. As x goes, let me draw it on the graph, sorry. As x goes this way, what number are we getting super close to? You can kind of notice it in your table as well. As I plug in larger and larger numbers of negatives into my equation, where is x getting super close to? Not negative infinity. If you want to, you can put it in your calculator. Plug in your equation. You can plug in like 2 to the 50th power. What do you get? Or wait, yeah, sorry, thank you. I was confused already, like negative. Negative 50, sorry, we're going to the negative. What does a negative power always do? Makes it a fraction. So we're going to get something 1 over 2 to the 50th power. That is a really small number, right? Which is also really close to 0. Yeah. As we continue to plug in larger and larger negative numbers, we're just going to get smaller and smaller fractions. That's the really funny thing about negative exponents, okay? I know this is confusing. We're going to do more practice, but this is just the first example, okay? So, as x approaches negative infinity, f of x approaches 0, okay? Is that making sense a little bit? And then as x approaches infinity, so as we go this way, what does f of x approach? Yeah, infinity. Okay. How are we feeling about this? It's a new concept, so it's okay if it's confusing at first. So we're going to do some more practice with this. But first, I have to introduce this idea of AH and K. Okay? Remember AH and K from your roots and rational equations? Same idea here. AH and K are going to be the same idea. So A is going to deal with its reflection, and then it's going to deal with your stretch and your compress. So depending on how big or small A is, so if you have an A that is larger than 1, it's going to stretch. And if you have an A that is a fraction, so between 0 and 1, it's going to compress, okay? And then if A is negative, that's when you reflect over the x-axis, okay? So then we have H, horizontal shift left or right. K is vertical shift up or down, okay? Just like we had AH and K in the last units, okay? Same ideas. They're just going to be in different positions here. But the same shifts and moves across the graph, okay? So, looking at, if you guys flip to the next page, page 358, looking at your top example 2. Example 2, we have f of x equals negative 1/2 times 3 to the x, or 3 to the x plus 4, and then plus 1. Okay. Again, these equations, they're going to be a little complicated. They're going to look scary and big and complicated. But the beauty of them is you can just plug them in your calculator. Okay? And then just make sure that you do things in the correct order and that you're only, whatever's in the parentheses. So here we have our b. So you have to see it. I would always put b and then the exponent into its own parentheses. So that exponent always just goes with b, okay? Make sense? So in this instance, our exponent only goes with 3, okay? So, what is our a? Negative 1/2. Negative 1/2. And then, what do we reflect across? The x-axis, because it is a negative a. And then are we compressing or stretching? Compressing. If we look back here, a is between 0 and 1. It's 1/2. That is between 0 and 1. So it is compressing. Okay? Good. What's our h? Not just 4. Look at your... It's okay, so x minus h is our original, right? Up here. X minus h. How did we go from x minus h to get x plus 4? We had to add what? How did you go from a negative to a positive? Yeah, it's a negative. You have to add a negative to get a positive. So our h is our what? Is what? Sorry. Negative 4. Okay? Make sense? So what does negative 4 do? It translates in our x and our horizontal plane. It moves it what? Left 4. It moves it left 4. Okay? All right. And then our k is what? Positive 1. And it translates in our vertical axis or direction, sorry. Our vertical direction is our k. Where does it move? It moves up 1, right? Because k is positive, therefore it moves up And then k is 1, so it moves up 1. Okay? Is that making a little bit of sense? Or at least this should be it should feel very familiar, right? We did this with the last unit. It's the same idea, okay? How are we feeling? Okay-ish? Yeah? Do we have any questions so far? Okay. So example 3, we want to find the value of k. So they gave us this graph, and they said that we want to find the value of k of the graph, which we know is going to be of the form j of x equals f of x plus k, where f of x is 3.5 to the x. So that's our parent graph, okay, in this instance. So we know that j of x is going to look like this. So far, this is all we know. But we got to add something. We got to add some k value to it, okay? And we know that 3.5 to the x power is our parent graph, which would be, I wish I could show you what that would look like in here, but that's my fault. It's not putting it up there. If you guys use some graphing calculators, can I put a graph here at all?
Yes, plus, and then you take graph.
Okay.
Plus page.
Oh, haha. Okay. Here we go. Let me just type it in real quick. F of x. Nope. F of x equals, and then we want.
You gotta close your parentheses on the x.
Oh, thank you. Equals 3.5 to the x power, which we need that, and then we need that. All right, there is your 3.5 to the x graph, okay? Looking at your graph in your book, it's on in the middle of page 358, and then looking at this graph, what changed? Not move up, but
From here to there.
if you were to look at, oh, are you saying from the one in your book to this one it moved up? Okay, cool. So yeah, from our original though, which way does it go then? From this one to the one in your book, what changes? It goes down. Yeah, it's opposite. Okay, so then, how do I get back to
Everyone bottom left?
the...
And then bottom left.
Oh, found it. Okay. Yep. Okay. Cool. Thank you. So it goes down. So that means we know our k value has got to be what? Negative, right? So the graph has been translated down, or we'll put down here. Down. And then if we flip back to this graph again, where does it cross on the y-intercept? The original. What value is that? Yep, it crosses at 1, right? Our y-intercept is 1. Where does it cross? Here. -1. So how much does it move down? It goes from 1 to -1. So it started here. How many units does it move down? 2. So the graph has been translated 2 units down. So k equals what? -2. So then our function we have the same base, f of x is the same, and we just add on our k, which is -2. Okay? You're not going to really have any problems like this, but the point of this problem was to practice recognizing how it moves from the parent graph, okay? In this instance, our parent graph was 3.5 to the x power, which is this graph, right? And it moved down 2. So it kind of just helps us recognize where it shifts and moves and how we can find our k if we're not given an equation, okay? So if this was a little bit difficult, that's totally okay. We just wanted you guys to practice it. All right. Okay. So then if you guys go to your guys' little graphs that you guys put in here, your little graph paper, we're going to do some practice real quick. We're going to do this together so that we understand the flow of how to make a table and then how to graph it, okay? So this one is pretty simple. It's just 5 to the x, okay? No h, no k, well there isn't, or no h and no k, okay? H and k don't really exist in this problem. So I'm going to plug in some x values, right? So I want you guys to all have calculators. If you don't have a calculator, I need you to go grab a calculator. Because what we're going to do is we're going to just plug these into our calculator so we can practice, okay? So if you don't have a calculator, go grab a calculator. Right. Because like the next one. Okay, everyone's got a calculator. Cool. So 5 to the x. Where should we always start plugging in? Where's a good number to start? I hear it. 0. Yeah. I'll just put this in like the center here. Okay. That's not the center, but that's okay. 0. And then we move out from there. So what's less than 0? -1, -2, 1, and 2. So this is a parent graph because there is no h and k, and our a is 1. So this is a parent graph. We can tell that just because it's a number to the x power. It's very simple, very standard. Okay? So with parent graphs, this is always a good place to start, from -2 to 2, okay? -2, -1, 0, 1, and 2. These are always good things to plug in. So let's plug in 0. What is 5 to the 0 power? Plug in your calculator if you need to. Five to the 0 power? 1. Okay. 5 to the first power? Had it last time. 5. 5 to second power? 25. Yep. All right, and then what's 5 to the negative first power? One over 5, which if you plug it in and you get a decimal, what do you get? Yeah, not 0.25, but yeah, 0.2. And then 5 to the -2 is going to be 1 over 5 to the second, which 1 over 5 to the second is what? We already did 5 to the second. What's 5 to the second? It's 1 over 25, which is also 0. Anyone plug it in their calculator? 0.04. Cool. All right. So now using those points, we can just take them to the graph and plug them in. So start with 0. We got 0, 1. Okay. 0, 1. Cool. And then we know 1, 5. So I'm going to go 1. Oh, 2, 4, 6, 8. Sorry. Got to pay attention to my units. 1 would be here. And then 5, this would be 1 here. 2, 4, 5 would be here. Okay? And then I got 2 to the 25, which would be way up here. I don't even have it on the graph. Make sense? And then I have negative 1 to the 0.2, which is really small. So like right here.
Not negative.
Huh?
Not negative. You got your y negative.
Oh, thank you. 0.2. It's like right here. Super small, okay? My dots are honestly too big for this graph. I mean, that's my fault. I should have made this graph smaller on the. And then we've got negative 2.04, which is like here, okay? But you guys get the gist of how to plug this in and then how to find our line. So then we just take our graph and it looks like something like that. That is a really bad line. But does that make sense? Are we understanding this a little bit more? Your homework, you're going to be doing quite a few of these problems, okay? Or something similar to this problem, and then identifying A, H, and K. Really quickly, we didn't get time to do this one, but we can start with this one tomorrow. I want you guys to just look at this one. Fun fact, this one's on your homework. So if you go and do your homework tonight, then you could work on it and have it for tomorrow when we do it together in class, okay? Or not, that's okay too. Okay. So tomorrow we're gonna go through this practice problem and learn how to graph it when we have an H and a K value, because it's gonna be a little different. So we're not gonna be able to start with 0 because 0 won't be the best place to start. So, homework problems are listed here, and then your test will be Valentine's Day, probably. I think we might have pushed it, and I didn't change the slides. I think it's...
Valentine's Day at the earliest.
Yes.
Probably later.
It'll be that week, though. It'll be Valentine's Day, which is Tuesday, so it'll either be Tuesday through Friday that week. Just know that, okay? Good job today, guys.